All of us have heard about glucose meters, but do you know what principle they work on?
Oh, no, I don't.
It works on the concept of a lab on a chip.
Is it? What is that?
So let's understand the working principle behind them. The first thing to understand is a plasmon. A plasmon is a collective excitation of the electronic fluid in a piece of conducting material. Just like ripples on the surface of a pond can be viewed as the oscillation of water molecules of the liquid. If you push down on the surface of the pond somewhere, the density of water doesn't change. Instead, the water elsewhere is displaced because the water has finite volume and pushes each other out of the way. Similarly, the electronic fluid pushes each other out of the way due to the Pauli exclusion principle.
So let's move on to surface plasmons. Surface plasmons are coherent delocalized electron oscillations that exist at the interface between any two materials. However, they must follow the following conditions so that the surface plasmons exist. 1. They must occur at the interface of a material such that the relative permittivity, real part, that is the dielectric constant, is positive on one side and negative on the other. Second condition is that the magnitude of the real part of the permittivity in the negative region should be typically larger than the magnitude of the positive permittivity, otherwise surface plasmons do not exist. Surface plasmons also follow the relation as shown. When the equality exists, we call that phenomena a surface plasmon resonance.
In order to excite surface plasmons in a resonant manner, one can use electron bombardment or incident light beams. The incoming beam has to match its momentum to that of the plasmon. However, for a given frequency, a free space photon has less momentum than a surface plasmon polariton. However, coupling of photons into SPPs can be achieved using a coupling medium such as a prism, using total internal reflection. In total internal reflection, the reflected photons create an electric field on the opposite side of the interface. The plasmons also create a comparable field that extends into the medium on either side of the film. This field is called the evanescent wave because the amplitude of the wave decreases exponentially with increasing distance from the interface surface. The evanescent wave has momentum greater than that of the incident light that excited it, dependent upon parameters such as angle of incidence, the refractive index of the two media, and properties of the metal film. By carefully tuning these parameters, we can excite a surface plasmon. In case of p-polarized light, this is possible by passing the light through a block of glass to increase the momentum. However, this is not possible in a s-polarized light.
Let us now look at the plot between reflected light intensity and the angle of incidence. The peak of this graph will correspond to total internal reflection, and the dip will correspond to the surface plasmon resonance angle. This is the angle at which the frequency and other parameters are correctly matched, so the incident light photons are absorbed and the energy is transferred to the electrons, which convert into surface plasmons, leaving a gap in the reflected light intensity. Under what all conditions can surface plasmon resonance be excited? One of the methods is frequency variation, that is, at a fixed angle of incident light, the wavelength can be varied until resonance occurs. This is known as resonant wavelength SPR and is not very widely used. The second method is the more commonly used method, that is when you vary the angle of incidence. This is also known as resonant angle SPR and it can be measured very precisely. This is what Varun had explained earlier.
So, enough of the boring theory. Let's talk about more interesting stuff. Let's talk about biosensors. What are biosensors? They are basically a device which uses a living organism or biological molecules, especially enzymes and antibodies, to detect the presence of chemicals. So, how can we use our above idea about surface plasmon resonance in the concept of biosensors? We know that changing the local index of refractions or other parameters changes the resonant conditions of the surface plasmon waves, leading to a change in the incident angle at which resonance condition occurs. This automatically suggests the idea of a sensor, since a sensor basically works on principle of that the changing the conditions of the system environment changes the response that the sensor produces. Hence, we can use them to sense the presence of biological molecules.
Let's dive into the details of a biosensor now. A glass slide is coated with a thin film of a noble metal on the reflection side. In most cases, gold is used because it gives an SPR signal at convenient combinations of reflectance angle and wavelength. In addition, gold is chemically inert to solutions and solutes which are typically used in biochemical contexts.
So let's look at the actual working mechanism. In this biosensor, a bait ligand is immobilized on the dielectric surface of the SPR crystal. Through a microflow system, a solution with the prey analyte, which is the green solution shown in the video, is injected over the bait layer. As the prey analyte binds to the bait ligand, and change in the resonance angle or resonance wavelength is observed.
After the dissociation time, a solution without the prey analyte, usually the buffer, is injected on the microfluids that dissociate the bound complex between the bait ligand and the prey analyte. As the prey analyte dissociates from the bait ligand, the surface shows the original minimum reflectance angle.
So, let's finally talk about the advantages of using surface plasmon resistance for biosensors. They provide label-free detection. What is a label? A label is any foreign molecule that is chemically or temporarily attached to the molecule of interest to detect molecule presence or activity, which can potentially alter its intrinsic properties. Thus, SPR provides us a label-free detection method and also provides us an accurate way of studying the concentration, specificity, binding, and kinetics. Thank you. We hope you found our presentation intriguing and informative. This video was presented by Varun and Narayani.